So the next presenter is Geraud from the Flatiron Institute, and he's playing around with Gromacs on Ookami. Please share your experience with us.
All right, can you see my slides? All right, so I'm going to talk to you about a code that is actually that likes to become the bear itself. So I'm Geraud Krawezik. I'm at SCC at the Flatiron Institute. And today I'm going to tell you about my experimentation with Gromacs. So first of all, the benchmark. So Gromacs, why did I choose that? Because it's a molecular dynamics code written in MPI and OpenMP. The nice thing about it is that it's a real life nature scientific tools. It does have SVE optimizations embedded. It also does not need to use a lot of memory per core, which is good for a machine that's limited to 32 gigabytes per node. And we already have results on x86 clusters, on GPUs, so that's pretty convenient. In terms of the benchmarking method, I used MG benchmark, which is something standard in this domain. So the idea is to have 15 minutes runs, and the metric that you use is nanoseconds of simulation per day. The nice thing about this benchmark is that it easily lets you change the runtime conditions, so the number of nodes, the number of MPI ranks per node, and then the number of threads, OpenMP threads used in each node as well. And finally, it just parses that and gives you nicely formatted results. So in terms of the systems I've used, so those are the inputs. So I used two of them. The one that you see jiggling here is a ion channeled. That's my benchmark because it's one of our user who is at CCB, Sonja Hansen. It has about 150,000 atoms. And then for larger problems, I went with lignocellulose, which is 1 million atoms. And that's something that has been created by PRACE, which is the European HPC partnership. And the goal in that was to test machines in the 10,000 cores and up. So now when it comes to let's go directly into what the versions I use. So I went with 2021.3. So usually you have up to 4 to 5 updates of Gromacs every year. Why this version? Was first of all, that's the one we use in production here at Flatiron Institute. So I have lots of performance numbers with it. But also, I noticed that with this version, when you have large number of ranks per node, it actually gets you better performance than what you used to see before. So that's why I decided to go with that one. The problem is that, as was mentioned before, you have lots of choices when it comes to compiler on this architecture. However, few of them actually work for Gromacs in this case. Out of the box, it's written for GCC. You can, however, let it work also with Fujitsu in cloud mode and with the ARM as well. When it comes to FFTW, I use the Fujitsu SVE implementation. So let's go directly into the results. So this is how it looks like, scalability numbers from 1 to 100 nodes. And what I did was I actually selected different configuration when it came to how many MPI ranks I'm using inside each node and how many threads to compensate, and the idea being to use all 48 cores and see what the result looked like. Sometimes there are holes in the data. That's because Gromacs cannot by itself find a good decomposition of the problem with the number of cores I'm passing it to. So here the performance total is actually about 97 nanoseconds a day of simulation. That's the max I was able to get that one. So the next step was looking into another compiler, which is obviously the Fujitsu Clang with its own version of MPI. The problem here is that it doesn't work out of the box. So the code has to be patched. Luckily, I found a user, Gilles Goyardet, who works at RIST in Japan, and he works on Fugaku, and he kindly shared the modifications he had made to the code with me. So I was able to actually run. And here we can see that under the same condition, the performance is actually 146 nanoseconds a day, which means about 50% improvement going from GCC to going to the Fujitsu compiler, which is pretty worth it. So now the next question is, okay, we have 48 cores. Fugaku, on the other hand, has more than that, as it was mentioned, and some of them are dedicated to the OS. So what if we don't actually use all 48 cores? So I went with it and decided to test with 46 cores, 44 cores, 42 cores, 40 cores. And lo and behold, the performance, the best performance I got was actually when I was using 40 cores in this test. And then I went from about 150 nanoseconds a day of simulation to 200-ish nanoseconds a day of simulation. So the big idea here is, if you can, and if that's required by your code based on the SVE that is used, go with the Fujitsu Clown compiler and be very careful to let some of the cores for the OS, otherwise the jitter will actually lower your performance. So this is how it looks on this machine. Now, what if we compare to what we would get on a regular x86 machine? So those are the results I had beforehand. So on the left is actually on our cluster of AMD ROM nodes, and on the right, that's actually on our Ice Lake. So you see that on the AMD ROM nodes, we get about up to 400 nanoseconds a day. The Ice Lake was about 250 and above. And then another interesting test is that NVIDIA have their own implementation and optimizations when you are using a single GPU node. So those are the results when it comes to V100 and A100. This used to be give you the best performance, but since they actually improved since 2021.3, now you can actually get better performance on a ROM node or on an Ice Lake node. So now we saw that.
Geraud, I'm sorry to interrupt, but if you could go back to the previous slide. If I'm reading this correctly, you were getting 200 and something nanoseconds a day on one Ookami node.
On 100 Ookami nodes.
Oh, 100. That starts to make a lot more sense.
Yeah.
Okay,
and so here to get, basically, that's the equivalent of 5 ROM nodes in this case.
Fine.
For this very benchmark. So that's why I decided to go to the next benchmark, which is something, it's basically doing weak scaling. And if we look at something that's way bigger than that, so that's lignocellulose. And on the left, I've put the results I got on Ookami, up to 100 nodes. And on the right, I've put what I see on I got on ROM. So here we got about 40 nanoseconds a day on Ookami. On ROM, I was able to get about 60, of course, with less nodes. But you see the performance going down on ROM. And I think that's actually due to the fact that basically they use a lot of collective operations. And since these ROM nodes have so many threads, so many cores, as a result, the more ranks you use, the more it's going to get messy. I'm testing that currently on more Ice Lakes and more Cascade Lakes, which actually happen to have also 48 cores. And I'll be able to give a better pictures in the coming weeks, obviously, depending on partition. So a couple of conclusions. Gromacs works, but the compiler selection is tricky. And that was one of the main issues to get things running. The problem size is very important for a medium system. 5 ROM nodes, which will actually give you the same performance as 100 nodes in this case. For the large system, however, things look better, and you could see that we also saw better strong scaling as we were increasing the number of nodes. Something I want to do in the future is look at LLVM 14 once it's stable enough, or at the ARM compiler, but ideally, I guess this will end up becoming one and the same thing. And thank you, Eva, Tony, Robert, Catherine, and Smith for the help and the discussions running on the system. Thank you.
Great, thanks a lot, Geraud. This was very interesting. Do we have questions or something in the chat? There's one question: whether Gromacs simulations pin to cores so the OS doesn't move them around?
Everything is pinned indeed. I'm using the OpenMPI stuff, and I'm making sure that nothing is moving around. So both on Ookami and both on the cluster of Intel and AMDs, everything was always pinned.
Could you comment a bit on how Gromacs is using the SPE instruction set? I have the impression that they're using the intrinsics, but...
So that's the thing, they actually define their own SIMD vectors, and then they go with that depending on what type of machine you are using. When it comes to, after that, using SV-enabled software, I went with the FFTW from Fujitsu because it has that. The thing is that when you look at the log file of Gromacs, it gives you a breakdown of what it has been doing. And it was using FFTW for maybe 5% of the time or something like that. So this does not have a significant impact at all.
And when you were comparing the executions from, say, A64FX with Robe or Skylake, did you see a shift in the balance of time between FFT and force field evaluation and so on?
I didn't see a difference there.
Okay.
Yeah. Same thing when it came actually to, for instance, the communication, etc. And that's why I really want to test on the Cascade Lake, since they have they should have the same communication pattern as Ookami, and then I'll be able to compare.
Interesting. And I was very impressed that you've got this good scaling with MPI and Ookami, because myself and others have found that rather challenging. So did you have to do anything special to get MPI to work well for you?
Not really. That was just using the standard things to pin processors when you are using both MPI and OpenMP, basically.
Okay, good. Thank you very much.
Thank you.
And Catherine also has one more question.
Oh, yes. I'm just curious because I know that on Fugaku they have one accessory core per CMG. So I guess they have 4 extra cores to take care of OS things. But it looks like you see it's fastest when you use 40 out of 48. So
there is also the problem of how Gromacs basically looks at 2 different kinds of interactions. You are going to have the ones that are with the atoms close together, and then the longer ones. So it can be either PME, that's the case of the ion channel, or RF, which is the case of lignocellulose. So it's going to actually divide the work between these 2 in different matters, and sometimes it can do it more intelligently. I chose to let it choose manually how to do that. You can actually go and tell it, hey, use this amount to do this and this amount to do that. I haven't played with these options because apparently few people look at them practically. But that could actually make it a result that, for instance, using 45 cores might actually work better, but then it becomes kind of tricky to set with MPI. Okay. Already, I mean, I have things like 42, you have 6 ranks and 7 cores and 7 OpenMP threads, you know, that's a kind of...
Okay, thank you.
Great, thanks a lot, Geraud.
Thank you.